Before we get back to the lectures, I hope you had fun in the midterm. We're going to set up a time in one of our classes, maybe next week, maybe the week after, maybe to review homework, review projects, review the midterm, go over all these things, because obviously it's not only important that we review all these things and you know all these things, but they're going to be part of the final. So we want to make sure that we learn from these experiences and we keep getting better, right? And by the time that we get to the final, that has more weight than the midterm, that we actually know how to do these things with our eyes closed. Yeah? All right. Any questions before I get going? Yes, the back. Can you speak up? I can barely hear you. This is the idea of the homeworks, not the projects. You want more homework? Every 1 second, any 1 second that? I think you're in the minority. I'm happy to give you more homework. Yeah, I agree. I agree. I would be really in agreement with you if everyone is okay with that.
We want to just know how will the questions in the exam. So
yeah, that's a little the purpose of this session, to review the homework and the midterm, to go over all the steps that are required for that for those type of problems. And the final exam is not going to be different than the midterm or the homeworks that you guys have done. I mean, it's in the same vein, right? Basic. I also have to say that I think that once you see this session that we're going to do, that you sometimes, not all of you obviously, but some of you, several of you, thought that the questions were much more difficult than what they really were, right? That
the point is, I read the book, the reference book twice every chapter, and the questions was like about what you written on the screen, and you see now in the classroom there is not many people show up, and then at the time of exam, I guess half of the class is not here.
Well, maybe 10% or 15%. Yeah, I can see the class is almost full. Yeah.
They watch. It is easy to watch your lectures, and since you have just your mindset is about the lecture, then you may do good in the exam. But if you just go through the book.
Oh, no, of course I agree, right? I mean, if you're not present for the lectures, it's going to be much more difficult than if you just read a book. I do try to follow the book that I mentioned, the textbook, as closely as possible, but obviously there are many things that are not covered in that book. There are many extensions that are not in the book, right? And the book is not strong or it doesn't cover homeworks or different types of exercises that you can practice on, right? So obviously all these things you have to be in the classroom. You're correct. You can go to YouTube and watch the lectures after the fact, but I think that these lectures on YouTube are mostly useful if you have attended the lecture here in class, if you have done the homework, if you have read the materials that I provide, and then you rewatch the lecture, right? But if you just watch the videos and expect, oh yeah, that's going to cover it, no, there is much more to learning than that. Otherwise, universities would have long disappeared, right? We just upload videos on the internet and we'll be done. So I agree with you. I agree with these things, and that would be the purpose. I also have to say that we're almost at the end of what that book can cover for image processing. So most of what we're going to see from today on, if not almost all of it, is not covered in that book. And I'm gonna keep posting, as I always do, the book chapters and the papers that cover these materials, but there's just so much. A single book never covers the whole topics that you want to include in a class. No, that's good. I'm glad. Please do.
That makes sense. If you have examination with main preparation based on assignment,
Yeah.
final project, then it makes sense to do more projects than examination.
Well, we're not going to do a lot of projects, right? I think we have done, correct me, 2 projects thus far. Is that right? So probably do 2, maybe 3 more projects max. That's it, right? So it's mostly going to be homeworks, and it's going to be obviously the final. There was another question?
Yes, so come back to his idea. He requires more homework. I agree with that. But some
We can do more homework.
The classmates maybe don't like that. You can an alternative way is that you can post some optional homework. If you have time, just go through it. If you don't have time, just ignore.
How is optional homework going to help you? I mean, that I post the answer, so I give you an optional homework with the question and the answer. Is that what you want?
Yeah.
Okay.
Because the previous...
Yeah, that's easy enough, right? We can certainly do that. Give you a few days to try to solve it and then post the answer. But, I know what usually happens with this, right? This is the same that the other student was mentioning, that you already have books for that, right? Where you have a lot of derivations and a lot of solutions for many possible questions. And the point is that that's not the practice that you need, right? The practice that you need is a real homework, right? Or a real project where you actually have to do the derivations yourself. You have to make the effort. Because if I give you a question and an answer, well, I mean, that's reading a book. There's just no difference. So that's not really, in my view, the best way. I can do it, there's no question, but that's not going to solve that, or it's not going to improve your learning. Make sense? Yeah? No? Yeah, question?
And upload some more materials about the next lesson, or if it doesn't cover in the...
Everything that I covered, it's in Canvas. Everything. It's always in there. If you go to Canvas, Carmen, and you go under Files, there is Handouts. There's a folder called Handouts, and you have all the handouts there. All these slides, everything that you do on the board it's most of it. It's also available in a slide form. So you have the slides of the class with the nice drawings that I can never make because I'm not an artist, right? I didn't do liberal arts. I decided to do engineering. You guys, and the drawings there are much better, right? So that helps too. But also you have all the derivations, and then I always have all the notes that you require for that. All these things are not in the book, obviously. Which, as I said, from now on, it's going to be most of it, right? All right, more questions? All right, let's get back to the lectures then. All right. So remember we discussed the shape from shading, and we derive a specific algorithm called photometric stereo. Very important algorithm, right? Something you certainly want to know how to derive before you get to the final. So the thing with shapeform shading, remember, or photometric stereo, is that you assume that only one light source is on at the same time, right? And that they go in a sequence, and that at each specific period in time, you have one light source on. This is called the local shading model. Let's say the shading model, period. Local shading model. And that model assumes that the light travels from the source, right, which we assume it's a point source, to the surface of our object in a straight line, remember? That's our assumption. However, when I measure the radiosity that I have at a three-dimensional point P, capital P, on my surface, right? That point is not only illuminated by the light source, right? It can be, even if I only have one light source, I could have multiple light sources, right? But even if I only have one light source, this point here, let's say this point here on the whiteboard, is not only illuminated by this light source, but it's illuminated by, say, that wall, right? Because a light source illuminates that wall, and the sum of that energy bounces back, right? That's why we can read radiosity in the image. And then eventually it hits that point, right? So the radiosity that we get is really due to the excitance that the light source emits and that reaches this point, plus the radiosity that is due to reflections or refractions on my environment, okay? And note that there is no distinction between what I observe due to the light source versus what I observe due to reflections of other objects, right? And these reflections can be defined by, let's see, I'm going to leave a lot of space here, so be careful, okay? So it's the radiosity that I have at a point Q, right? So if I'm measuring the radiosity here at point P, I have to consider the one that comes from any point possible, any point Q, right? So let's say that point Q on the wall, and that reaches here. I need to multiply this by, obviously, the solid angles. So I have the cosine of the angle with respect to the point P. This is a foreshortening for the point P, and the cosine for the point Q divided by, remember, pi times d pq square. That's the distance from P to Q, okay, this term here. It's the distance from a point P, say that I have a surface here and another surface here, and I have a point Q here defined by this normal, and a point P here defined by this other normal, and then I have this distance from P to Q right here. Okay. And of course, this is my angle for the point P, my foreshortening for the point Q. Right? Okay. Now, I'm going to multiply this by the albedo of my point P, right? And now I need to sum over all the possible Q's over all my environment, right? So how many points are there in my environment? Infinite, right? So I'm just going to integrate, right, in my world. And then I'm going to have just one more variable, let's call it V, PQ, where V of PQ is equal to 1 if P sees Q. By seeing Q, I mean that there is a direct line, right? Straight line from P to Q that is not obstructed by any object, right? So that the light leaving Q can reach P, and 0 otherwise. And this is differential of area in my point Q. And this is just a very simple way of extending the algorithm that we've seen of shape from shading to include additional elements or information illumination of the environment. Okay? So far, so good? All right, now I'm going to ask a very interesting question, I think. So imagine that I take an image, right? This is my image. Now remember that my image is given by a certain number of pixels, right? So I have columns and rows, and those define the pixels, correct? Right? That's what we've always done, or what we did at some point where we're computing point correspondences, for example, right? And when we're computing point correspondences, what we said is, okay, I can convert this image into a vector. Let's call it X, right? And what I'm going to do is I'm going to take the first pixel right here and write it as x1, the first element of that vector, right? And then I'm going to take the second pixel, I'm going to write it down as my second element of the vector, and so on up to the last element of the first row. Then I'm going to turn to the first element of the second row, right? And so on and so forth up to the last element of the last row, right? I'm going to create this vector, this feature vector here of pixels, right? Pixel information. That's what we did when we computed the correlation between different pixels, right? Or different windows around the pixel to find point correspondences, remember? Okay. But the difference now is that I do this for the whole image, right? And I'm assuming this is an image of an object, right? Now, remember that I have whatever object, maybe I have an object like this, right? This marker. And I place it here on the table, right? And I put my camera here on top, and I take pictures of that object, but they have multiple illuminations, right? And every time I turn on one illumination or one light source, and I turn off all the other ones, and then I turn that off and turn another one on, and so on, right? So I take multiple images. So this would be image 1 with the first light source, and I can go on up to image n. Now, in theory, right, at least in theory, n can go to infinity. Correct? Because I can have an infinite number of possible light sources, right? So far, so good? Following me? And every time I take an image, I obtain a different feature vector like this. So let me call this x1. So that would be x11, x12, x1p for the first feature vector, or the feature vector represents the first image. This one here would be the last one would be xn, which is xn1 through xnp. Yes? Okay. Now, note that these vectors, these xi's, are defined in the real space of p dimensions, right? These are random vectors, right, that I can define in a space of p dimensions. So, if my image had 2 pixels, just 2 pixels, right? This is the worst camera ever, I know. Well, the worst one would be 1 pixel. Let's say the second worst camera, it has just 2 pixels, all right? So with 2 pixels, each of these images would be defined by a 2-dimensional vector, and therefore, I could define these vectors in a 2-dimensional space, right? Say R2. And then x1, this x1 here, it's going to be, say, this vector right here, and x2, maybe it's going to be this other vector, right? And so on. Now, usually we do not draw vectors like this in these spaces, in a vector space. We usually just draw x1 as a point, x2 as a point, xn as a point, right? And the reason for that, remember, is because instead of writing the coefficients, say alpha 1 E1 plus alpha 2 E2 plus alpha p EP, right? Instead of writing vectors like this, where the EIs here are the basis vectors that define each of these dimensions. Remember, we went over this? Instead of doing this, we just write down the coefficients, right? That's how we simplify the vectors. And that's the same as saying, okay, this one has this coefficient here and this coefficient here, and therefore I just put that dot there representing the coefficients. Okay? So far, so good? All right, we're making progress. So, what I have now, instead of having this in 2 dimensions, because I have p pixels, now remember, p pixels in a camera, in a modern camera, can be 10, 15, 20 million pixels, right? Easily. So, instead of defining a space in R2, you're going to have a space in R 10 million or 20 million. Right? But otherwise, that's the same thing. Now, don't try to visualize 10 million, right? 10 million dimensional space. It's impossible to visualize a 4-dimensional space, let alone a 10 million dimensional space. Right? Can't get your head around that. But you know that it exists and that it's nothing else than something like this, right? Okay? It's just a vector space where the basis vectors are orthonormal to one another. That's it. All right. Now, again, remember where we were. I have my object, and I put it on a table, and then at the very top, I put a camera, and I take pictures of that object. And every time I take a picture, I change my illumination, right? The position of the light source changes, right? Now, I can take an infinite number of pictures because I can put my light source at an infinite number of positions, right? And my question is, all right, every time in now, not R2, but in, say, my space that is going to be RP, maybe P, P maybe in the millions, right? Now, every time I do this, I'm going to get a an image that is represented by a feature vector like this, right? Right? Now, consider that feature space, right? That vector space right there. That vector space can represent all the images you can ever take. If I take an image that is completely black, right? I have absolutely no illumination and I take an image, right? The image is, all the pixels are at 0. Then the vector is going to be right here at the origin, right? If I take an image of, say, the marker, maybe under certain illumination, it's going to be maybe this point right here. If I take an image of another object, right, of a cell phone here, right, take an image of cell phone, then that's going to be another vector, you know, maybe over here, right? Every possible position in that vector space represents an image of something. It can be of random noise, right? If you have an image of random noise, that's still represented in that vector space. Now, the images that I have taken of a specific object, just one object, but under all possible illuminations, cannot cover the whole space, right? Obviously, because that space includes all the possible images of all possible objects. Yes? So if I take images of just this one object under all possible illuminations, all of them, what is that subset going to look like in my vector space? Just think about this for a second. Do you think, so again, let's think that my vector space has, I have a camera that has 20 million pixels, right? So my vector space is R to the 20 million. What would be the subset within that huge space of all the images of a single object under all possible illuminations? First off, you may think correctly that it may actually define a subspace of that space. A subspace would be a space of lower dimensionality than your original vector space, right? So if you start with 20 million, maybe you can define, or maybe the images of this object under all possible illuminations is going to be defined in space of 10 million. But you don't need 20 million dimensions to define just one object, right? This seems, we still don't know why, but this seems reasonable. You agree? But the question is, how many dimensions will my subspace have? Anyone wants to make a bet before I give the answer? Before I derive the answer? Just a guess. No one wants to guess? You're not going to lose any points. You're not going to gain any either, but maybe satisfaction that you got it right. Anyone wants to make a guess or an educated guess? No? 10? Do you want to elaborate why? Or it's just a guess? No? Anyone else? 500, why? You go in the right direction, so you think it's a low number, right? You can intuitively see that if I take images of just one object, even though the number of possible illuminations is infinite, right? That all of these images have to be constrained into some type of a smallish space, right? It makes it, because the whole space can represent every single object under every possible illumination. All right, so let's see how this would work. To do that, let's consider a very simple object. So how about if I consider an object that has only 3 different surfaces, and by different surfaces I mean that a surface has the same normal, remember, right? Each surface has a normal, and therefore I only have 3 different normals. So let's consider a very simple object like that. Let's consider an object that looks something like this. Okay, this is a plane, right? This is a plane like this plane right here, right? So this could be it, right? This plane. And I'm going to have another plane here, another plane here. So I have another plane, say, here. Okay, let me see if I can do a better drawing of this. Okay. All right. So the idea, drawing these things in 3D is a little tough, huh? The idea is that I have a surface like this, right? And then one like this and one like that, right? So I have 3 surfaces, okay? Okay, so maybe I can do better. Let's see. Maybe if I do it like this, it'll be a little clearer. How about that? It's probably a little better. Okay, now I'm going to add a camera, right? So as before, I'm going to have my camera up here so that I can take an orthographic view of this. Now a point P here, my point capital P, is given by my normal. Remember, the normal is what defines the shape of the object. So the normal at point P. I have my source. Let's call it S. And therefore, I have my vector here, SP. That is the vector that defines the source of that point, right? So now I know that the normal vector has norm equal to 1, obviously, and the source vector has norm equal to epsilon squared times the exitance, right? Remember that? Our shading model. Okay, so now let me define a matrix B of the radiosity. Remember, that's what I can actually see from the camera, the radiosity or the intensity that's proportional to radiosity, right? The radiosity, what is it going to be? All right, let's define for every pixel, right? So we said we have how many pixels? P pixels, right? So I'm going to have, it's going to be, let's start with the normal. So I'm going to have the normal at the first pixel, right? The normal at the second pixel, and the normal at the P pixel or nth pixel, whatever it is. Let's say N because my notes say N, okay, or P. Okay, let's say P. So I already start with P. And now I need to multiply this by the albedo, right? The albedo at that point or pixel. And I create this matrix. And now my image, right? X is going to be, remember my image. My image is equal to this matrix B times this vector S. Now remember, S, it's the same for all the pixels because, or all the points, because I'm assuming that the light source is at infinity, right? So this is B times S. And now I'm going to take, remember, the maximum of this and 0, right? Because if the camera or the light source does not see that pixel, then it's 0, right? If the light source cannot illuminate that particular pixel. So far, so good? Doing good? So that's the model that defines all the images. Now, by changing S, I can create all the images under all possible illuminations. You agree? But look at this. What is the dimensionality of X? The dimensionality of X is going to define the subspace in RP. Okay? Well, the dimensionality of X is going to be given by the rank of B. B times S or B, right? But B times S, what's the rank of B times S? This is 3 by P, or P by 3, and 3. So the rank is going to be maximum is smaller or equal than 3. Right? Which again, if the rank of that matrix can only be 3, then the number of dimensions, right, that I can define in my X space can be at most 3. 3, I'm going to repeat that. The subspace in my space RP that defines all the images of an object under all possible illuminations is at maximum of 3 dimensions. That's insane. So let's find that the space. I'm really interested in finding that subspace, aren't you? This is really cool. All right, let's see how we can find that subspace here, right? The subspace that I have here, which I know is going to have dimensionality 3. Let's see how on earth I can find that. Now remember that if I want to extend this to more than one light source, that is not going to change my result, because I can define the number of light sources, say from 1 to k, and it's going to be the max of B times Si, right, for each of the light sources, comma 0, and that's exactly the same. You can also extend this, if you will, to the continuum that we have done before for all the possible illuminations. So this is going to be the integration of the max of Bs0 ds, right? Same thing. All right, so I'm going to call this product that defines the illumination or the result of all the images that I can have of a specific object under all possible illuminations. I'm going to call it this weird L. Okay? So this L corresponds to all the images, all images created by all possible illuminations. Okay. So I can define it formally as all my images X, where X is equal to B times S for every possible S. Now, how am I going to define all the possible light sources? There's a very simple way that we have used that we have used before, which is all the vectors in R3. Good. Okay? Because if I'm in 3 dimensions, all the possible vectors here in 3 dimensions define first all the possible directions for all the possible light sources, right? And the norm defines all the possible excitance solid angles and foreshortening, right? Okay, wonderful. So we know, we've said that the dimensionality of that set that I have is equal to the rank of B, which is smaller or equal than 3. Okay. When is it 3 and when is it smaller than 3? Anyone can tell me when I'm going to have that rank of B being smaller than 3? Anyone? Look at the definition of B. No, that's not what I'm asking. I'm computing the rank of B, right? So the rank of B is a maximum 3. It's 3 in one condition and less than 3 in other conditions. And I'm asking you, when is it less than 3? So if it's only on a plane, what happens? Not one dimension, but what happens? That these normals are? No, they're all the same, right? Right? And then in that case, if they're all the same, they're linearly dependent, and the rank is equal to 1. If I had two surfaces with two different normals, then the rank is 2. If I have 3 or more surfaces, that's why I have 3 here. Right? If I have 3 or more, then they're all linearly dependent, but because this is p by 3, it doesn't matter how many p's I have. You know, after 3 by 3, the rank can only be 3. Cannot go beyond 3. It doesn't matter. Remember from a structure from motion, we had the same deal, right? Once you have more equations, it doesn't matter. The rank is fixed by 3. Just the number of columns is not going to change. So after 3 surfaces, it doesn't matter. We have 3, 4, 5, 6, 7. The rank is going to be 3. Okay. So let's see how, again, we can reconstruct this. To begin, let's assume that my light source, let's simplify this model that we have here just a tiny bit for a second. Let's assume that our light source is right here in the same location as the camera, okay? So it illuminates orthographically this plane. And I'm going to call this set that I obtained, the set of images with this light source, I'm going to call it L0, which is going to be equal to L. But now, because this light source, you see, illuminates every single surface, all the pixels are going to be different than 0. So it's going to be this intersection with x in RP. Okay. Meaning that all the xij's that I have here are going to be different than 0, right? All right, L, this L here, obviously defines a subspace of 3 dimensions. A subspace, it's a convex set. Right? Remember what a convex set is? That if I have 2 elements of the set, for every possible 2 elements of the set, the line that connects them, it's also in the set. That's a convex set. Right? So obviously a hyperplane is a convex set because any 2 elements of that plane or that hyperplane is in the plane or hyperplane, right? And because this is this union, this is also convex, obviously. So these are all convex sets. Obviously, they are linear as well because we're defining linear combinations here. To see that, you can also say, let's see, I could say, let's do this. I could say that if x is in L0, then alpha x has to be in L0 too, right? It's linear, right? You agree? Because L0 includes all the images under all possible illuminations. So if I have one and I just multiply by a scalar, right, with alpha larger or equal than 0, then that new vector has to be, that new image has to be in the set. Okay, let's define the illumination sphere. I'm going to start by attempting to draw a sphere. Now, bear with me, that's my best attempt to drawing a sphere. Or S2 on a two-dimensional plane, right? So you're going to have something like this, right? It's a three-dimensional or two-dimensional sphere, S2. And this is S2, right? Defined in 3D space. Now, if I have this and I have my object, right? My three-dimensional object right here, say at the center, right? I center the object at the origin of that sphere. This is the same object that I have drawn here, right? Same one. Then if I do this, that defines a hemisphere, right? When I do this, right? Say this normal right here defines this circle, right? This circle right here defines the cat that is orthogonal to that normal, right? That is called a great circle because it covers the whole sphere. And that great circle defines this hemisphere, right? This top part here is a hemisphere, right? I have cut the sphere into half and I have a hemisphere, right? And that is a hemisphere that we've seen before that determines all the possible illuminations that can come in that illuminates that specific plane. Yes? Okay. Now, if I consider now the other surface, that's this one here, that has this other normal, this one defines another great circle, right? This one right here, that defines this other hemisphere right here, right? And if I consider now this third one, that's given by this third normal, that defines yet another great circle that defines yet another hemisphere. You see how this works? So every surface that I have with a different normal defines a different hemisphere that's carved out of this 2D sphere S2 that I started with, right? So let's see that. I can actually draw this three-dimensional sphere here, right? This 3D sphere. And now I can define, say, this great circle here, this one here, and this one here, maybe, right? And now this carving is given by all the hemispheres that I have here. And note that I ended up with a number of cells here that I can now number, right? I can call them as I, as J, and so on. If we only have one normal, right? Let's assume that, as we said before, we only had this first surface here. We only had one normal. How many cells am I going to end up with? How many these separations? 2, right? S1 here on top, S2 here at the bottom, right? So this is going to be 2. What happens if I have 2 normals? How many cells am I going to end up with? 4. Very good. 4. In general, you're going to end up with, if m is a number, say m, the number of normals, then you're going to end up with m times m minus 1 plus 2 cells. Okay? And obviously, here, obviously, m has to be smaller or equal than p the number of pixels, right? I cannot have more normals than pixels. I could have every pixel representing a different surface with different normals, but I can, the p is the maximum. All right, I'm going to use S0, let's say that S0 is right here, to represent the illumination that yields L0, this one right here that I had defined, which, remember, is illumination that illuminates every single pixel or every single point on this, all the surfaces, and therefore every single pixel in the image. Okay? So none of the pixels is 0. The other sets are going to be the LIs, with Li is given by the illuminations in Si, the SIs that I have carved out here. And then of that, I'm going to take the image, Pi. Pi is the image of my set Li, which is going to be equal to the maximum of B times S, or 0, right? Given that S is in Si. And now remember that because this is linear, I can multiply this by any alpha, right? So I multiply this by any alpha, and alpha has to be larger or equal than 0. Okay? And this are the images that I can take for every single light source that I can create, right? So the different illuminations that I can actually obtain is limited by the number of normals that I may have, which is limited by the number of pixels that my image has, right? Okay. Now, the okay. The dimensionality of these new sets, it's still smaller or equal than 3, right? Same as before. Also note, this is just a detail, but note that the image of the L0 it's equal to L0, right? Because there's no pixel that changes because all the pixels see, or all the points in L0 see the light source, right? So that doesn't change. All right, so finally, let's write down the set of all images under all possible illuminations. So let's call this set, I know, U, for example. So U, it's going to be, that doesn't work. U is going to be all the images of an object under all possible illuminations. U is going to be equal to X. X, remember, it's the maximum between B times S or 0 for every possible S in R3. And this is the same as the union of I from 0 to M minus, or M minus 1 plus 1, and PI LI. Okay? That's what we've defined. This is right here. We have to remember this for Lambertian surfaces. Right? This is the underlying assumption in the shading model that we have used, that we created early on. Illuminated by a single point source at infinity. Okay? Now, if we want to consider other light sources, as we have done with the model that we started today's lecture with, then we can easily extend that with, let's call it C, all the x's, x equal to the sum now of I from 1 to k of the max b times si, or 0, excuse me, where si's now are three-dimensional vectors, and we have to consider here for all k as a positive integer. Okay? Okay. Now, let's look at the final set that we have created. Now, remember, this is convex. This thing here is therefore convex, right? So the set here is convex as well. But I can now multiply this by a scalar, right? I have done before. Where have I done this? I know this is somewhere. Did I erase it? All right. Anyways, we had done this before. Remember that if X is in my set Li, then alpha X is also in that set, right? Okay? Yes? All right, so let's note not only that this is a convex set, but what type of convex set this is. Now let's start with lambda equal to 0, and let's go back to our terrible, awful camera of 2 pixels, right? So, because I only have a 2-pixel camera, I'm in 2-dimensional space. And now, if alpha were to be equal to 0, that would be represented by a 0, 0 image, which is given by this vector right here at the origin, right? Yeah. Now, if alpha is very small, right, 0.000001, right, then that's going to be a small number about the x direction and a small number about the y direction, right? So this is going to start growing. This is going to start growing like this, and this is going to start growing like this, right, in this direction, right? I'm going to keep growing this in both directions, right, in both these directions, and I'm going to end up with a shape like this. And a shape like this, it's called a cone, okay, where you have alpha x. So C, right here, this set, is a convex cone. And in fact, we can say is a 3-dimensional, remember, or less, convex cone. This is called, in the literature, the illumination cone. Super cool. All right. Now, typical question that I may ask, right, in a homework or in an exam. What is the minimum number of images that I need to compute the illumination cone? Three. Very good. Why? Because I have a 3-dimensional cone, right? So obviously the minimum number is going to be 3. Right? Remember back to structure from motion? Same thing, right? Now, if I have more than 3 images, can I still solve the problem? Because remember, the real world is not Lambertian, and I don't have lights at infinity. No matter how far away they are, even the sun is not at infinity, right? So, believe it or not, the world is slightly different than what we have modeled here. So the equations I'm going to end up with are not going to give me a unique solution. In fact, they're not going to yield me any solution, right? Going to be 0 solutions. You agree? But do we know of a method that we could use to solve this problem? Linear least squares, yeah. So I can actually use linear least squares to find the illumination cone. How about that? So given a number of images of an object under different illuminations, I can compute the illumination cone. What does this mean? It means that I can compute that subspace, well, actually, it's a convex set. It's a cone, right? So it doesn't look like this. In fact, it looks something like this. So if I'm here in 3 dimensions, it will look something like this, say, right? This is a plane. So if I have this 3-dimensional space right here, it's going to be, say, a plane like this, okay? But defined as a cone, right? So if I have enough observations, say a certain number of images, I can use linear least squares to estimate that illumination cone. And now, that illumination cone defines all or includes all the images of my object under all possible illuminations. So after 3 images, really, if I already have 3 images, right? Really doesn't matter. Obviously, if I have more, I'm going to get a better estimate of the cone, right? But once I have a good estimate of the cone, it doesn't matter if I keep adding images because I already know what every other image I can ever have is going to look like. They're already defining that cone. So now I can render, can generate any image I want under any illumination I want. They're all defining that cone. It's insane. So have you seen these effects where they'll show you an object and then they'll keep varying the illumination back and forth in multiple directions with multiple lightings and so on, right? Simple. Once you have the illumination cone, you can start creating really cool effects. Okay? Now, there are extensions of that, obviously. You could define multiple illuminations by just applying the code multiple times, right? And then adding up the results as we've done today, earlier today in the general model, right? The global model. And there are extensions of the cone that use some nonlinearities or some more complex mathematics to get even better estimates of that, especially for non-Lagrangian or non-convex objects. Okay, because if you have a convex object like the one I've drawn, everything looks really nice. But if you have a concave object like this, right, where the light source starts bouncing back and forth, then all these shading models that we've defined break apart, right? So there are extensions for that, because obviously, if my object looks something like this, and I have a light source here, then this is a nightmare scenario, right? The lighting will keep bouncing back and forth, and that will break down my equations very quickly. All right, so let's see how I can derive the actual algorithm to define the illumination cone. So to do that, I'm going to do a 2-dimensional example because I only have 2 dimensions on the board. So instead of working in the 3-dimensional world, I'm going to work in this 2-dimensional world instead, okay? But the same applies to 3 dimensions. So let's see that. See how we can do this. All right. Again, this is the illumination cone for 3-dimensional worlds. A 2D example. So imagine the object that we have used until now. But now what I'm going to do, you have this 3-dimensional object here, right? And I'm going to smash it using orthographic projection. Remember orthographic projection, right? And I'm going to obtain a 2-dimensional object. Looks something like this. into the space. My camera is here on top. I have a light source somewhere, right, that I move around in every direction to illuminate this, because I'm in 2D, can only move it in these directions. I have this normal here, this normal here, and this normal here. So I have 3 different normals. Let's call them N1, N2, and N3. I also have my SIs. Remember, the SIs correspond to the set of illuminations that change the image, right? The number of points or normals that I see, okay? Now, let's see. S0, remember, okay. Let's try this one. No, all right. S0, remember, it's the set that illuminates every single point on the object. That is going to be over here, right? So when I have the light source here in this region, this sees every single normal, right? But after I have moved, you see this plane right here in this direction? After I've moved beyond this point, which defines this plane, then that light source here does no longer see this surface, right? Okay. And once I've moved beyond this point, this light source here does not see this surface. So this is the area of S0, okay? Now, there's another area right here, which defines then this other surface, right? Once I move beyond this line, this light source does not see this or that. So I'm going to call this, this I'm going to call S1, S2. So I'm going to call now, okay, let me see, this one here, S3 and S4. And now once I move beyond this point and that point, the light source here and here, right, do not see this one, or that one, right? They are behind, they are underneath the object, right? So if I'm in the hemisphere, I'm under the hemisphere, so the surfaces on top don't see anything. So I'm going to call this S5, okay? So far, so good? All right. So the region S0 specifies, oh, there they are. It specifies my L0 set that I have given before. S1 specifies L1, S2, L2, and so on. Let me call this surfaces here B1, B2, and B3 for the 3 different B's that I can have. Remember, B, assuming that this is lumbertion and the albedo for all these points is the same, right? This B value is going to be constant for every single surface. And therefore, Xi, the image that I can have for that surface, is going to be equal to Bi times S. Okay, Xi, a point in the ith surface. Okay, any point, doesn't matter because they're all the same. So what that means is that this image, right, the image can be represented with just 3 points or 3 values, x1, x2, and x3. Correct? Because every single pixel on that surface is exactly identical. Every single pixel in that surface is identical, and so on. So with just 3 numbers, I can represent the 3 different surfaces. Okay. So let's go back to our three-dimensional space. Let's say that this axis here defines the value for my first element, x1. This one here defines x2, and this one x3. And now I have, again, remember what I did before. For this three-dimensional coordinate system, I have a plane, hyperplane, right here, right? In that case, a two-dimensional plane, right here that cuts. So this is going to be my plane here somewhere. Okay. And this intersection that goes like this is my illumination cone. Okay. My L0. Okay. Now, this plane here defines all the other L's, LIs, right? All the other LIs are somewhere here. But remember that when I take pictures, what do? I take the projection of the LI, right, on the image, which means that if that Li does not see, that's defined by an SI, right? Each Li is defined by an SI. If that Li is defined by an SI that does not see specific surfaces, that pixel xi is going to be equal to, like xj, right? It's going to be equal to 0, right? Okay, so let's see. For this one right here, S1 or S2, right? When I move here, then that pixel, right, is going to be equal to 0. When I move here, this pixel is going to be 0 and 0. And when I move here, this is going to be 0 and 0, right? So let's represent this in that space. When I project this onto the image, what am I going to get? I'm going to get, I lost one. Okay. Oh, there it is. I'm going to get x3, right? So when I'm here, I'm going to get x3 equal to 0, right? Which means that I'm going to have this cone right here, right? This area, right? Which is now, I have this plane, and I project it, right? I bend it, I project it onto that plane defined by x1 and x2. And x3 for that plane right here, x3 is equal to 0, right? And I can do the same here, project it here onto the plane defined by x2 and x3, and x1 now is equal to 0. For these other additional spaces, x2 and x3 are 0, and x1 and x2 are 0. So x1 and x2 0, so I'm only going to have this axis, right? And here, only this axis right here, right? So the cone is going to be, it's going to look something like this, right? Oops. Okay, let's see if I can draw this a little better. The cone is going to look something like this. And again, you have better drawings on the slides as usual. And then like this. And like that. Okay. So this is on the plane defined by x1 and x2. This is on the plane defined by x2 and x3. And this is somewhere in midair, right? So that defines three surfaces, two on the planes defined by x1, x2, x2, x3, and the other one here, somewhere in midair, right? Between x1, x2, and x3. And that defines a cone of 3 dimensions. Okay, well, in that case of 2 dimensions, because obviously I'm in 2-dimensional space. Okay. So that's the illumination cone. right? That's how you compute it. We can put this into words as an algorithm. To do that, let me call this right here is the projection of L0 onto the image. This one is the projection of 3. This one, I'm not sure, 3. Oh yeah. This is the projection of 2. Okay? And you could go on with this other one that's defined here, and this other one that's defined here. But because these two final ones, which correspond to L4 and L, actually this is 1 and 2, I was right. Okay. This is 1 and 2. And then it would be 3 and 4 right here, right? But because 3 and 4 are already defined within the other ones, then I'm going to ignore them, okay? Make sense, right? Okay. So with that, let us define the set C, the illumination cone, as the union of these PIs. And I'm going from 0 to 5. Okay? And that's what we want to get. So let's define this in an algorithm. Oops, I think I'm out of time. Okay, I'm out of time. I'll define the exact algorithm, which is, interestingly, you can implement this in like literally 5-6 lines of code in MATLAB, right? So that's what it takes. It takes you to get images under different illuminations of an object, 4 or 5 lines of MATLAB code, and that's it. With that, you can, with these 5-6 maybe lines of code, you can generate as many images under as many illumination conditions as you want, right? It's that simple. Because it's just basic linear least squares, right? And we know how to do that. All right, I'm going to do the details of this next time.